Hello and welcome to another section of the Geology 1 Processes and Products Lab DVD. My name is Renee Clary and today we'll be talking about glaciers and glacial processes. Just like some of the other processes that are discussed in Geology 1, a physical geology class, glacial ice is also a geologic agent. Geologic agents change the surface of the earth by eroding, transporting, and depositing. And as you might guess, glaciers are the most powerful geologic agent there is. They're not the most effective geologic agent now because we're not in the middle of an ice age, or at least we're not covered with a lot of glacial ice. But in the past, the glaciers were more important as far as agents of erosion, transportation, and deposition than they are today. There are different types of glaciers. In general, we usually divide glaciers into two different types. Some textbooks, however, will give you as many as 4. However, 3 of them are more or less associated with an alpine system. An alpine glacier is simply a river of ice. It stays within its glacial channel or its glacial trough. A cirque is a bowl-shaped depression at the top of the mountain. This would be a cirque glacier when it's filled with ice, and when the ice is melted, we also use the term cirque to describe the erosional depression. We'll look at some pictures of that in just a minute. So we have an alpine glacier, which is a river of ice. We have a cirque glacier, which would fill that bowl-shaped depression, usually toward the top of the mountain. And we have a Piedmont glacier, where 2 or more glaciers can merge at the foot of the mountain range. However, all of these are associated with an alpine or valley glacier system. Here we see a photograph of a glacier taken in Alaska. Here is our main glacial trough or channel. Here's our river of ice. It is an alpine glacier, and we also see some tributaries, other glaciers moving into this bigger glacier or the main glacier here. Up in the top of the screen, you can see a bowl-shaped depression that's filled with ice. It's kind of semicircular. This would be a cirque. The other type of glacier is a continental glacier. This is a large ice sheet, and it's not confined to a valley. In fact, the ice moves just about anywhere it wants to. Now, in the past, continental glaciation was much more common than it is today. Today, we only see continental glaciers in 2 areas, Greenland and Antarctica. Here you see, and again, this isn't to scale because Antarctica is much bigger than Greenland, but you see an overhead drawing, an overhead map of Greenland and the surface that is currently covered by ice. You can see that the glacier is not confined to a valley. It covers most of this landmass. Here is a cross-sectional view, and you can see that the glacier is filling most of that continental mass. Now, what's unusual about Antarctica, if we move to the right side of the diagram, we see that we have a lot of ice covering the continent, which is, of course, centered on the South Pole. If we look at the topographic view here, the cross-section, we see that the glacial ice actually covers a mountain range, the Transantarctic Mountains. We don't see those poking above the ice here. This continental glacier covers the entire continental landmass. Now, let's talk a little bit about a glacial budget. In a glacier, in an alpine system, we have 2 zones. We have a zone of accumulation and a zone of wastage or ablation. This is pretty parallel to what we see in a groundwater system as far as a zone of aeration where we have water and air in the pore space, and a zone of saturation where we have just water in the pore space, and of course the water table would divide those 2 areas. In a glacier where we have a zone of accumulation, we get more snowfall added to the glacier than that melts during the year. So we're keeping the snow coming, we're adding ice mass to the glacier, it's not melting greater than what's being added. Now, the zone of ablation, or the zone of wastage, is the area of the glacier where we're losing more ice mass than is being accumulated. Now, we can lose that ice by calving off some icebergs as the glacier reaches its terminus. We can also lose ice from melting. We can lose ice from sublimation, where the ice moves directly into the gaseous form and doesn't even go through the liquid stage. So this zone of accumulation and the zone of ablation, or the zone of wastage, are separated by a line which is known as the snow line, the firn line, the snow limit. Those terms are pretty much interchangeable. Firn line is pretty common. Here we see zone of accumulation, the snowfall exceeds the losses. Zone of wastage or ablation, we're losing more than we're gaining. And firn limit, you can also see firn line, snow line, or snow limit. That's going to separate these two areas. Let's take a look at that in an overhead view. Here we have a glacier. In this part up at the top, we get more snowfall than the ice we lose by melting. In this bottom piece, we are losing more ice, either by calving off these icebergs down here, or melting or sublimation, than we're gaining through snowfall. The imaginary line that separates accumulation from wastage is known as the snow line or firn limit. Note some of these dark lines moving through the ice. These are crevasses. These are deep cuts or deep gashes in the ice. We'll look at those up close. We can see that as a glacier turns here, we may see crevasses developing on the outside of the curve. Also, as glaciers move over perhaps a little bump in the road, we end up with more crevasses as well. When we are actually compressing the ice, maybe moving down into over this little high and into a flat zone, we can see closed crevasses that were originally opened in this area. Here's a photograph showing some of these deep crevasses. Some of them can extend much more than 100 feet, especially in Antarctica. Very dangerous, especially when a snowfall covers and you cannot see the crack or the crevasse that lies below. Okay, glacial ice is a geologic agent, and therefore it will erode, transport, and deposit. Let's look at some erosional features first. Because glacial ice will often pick up little pieces of rocks, sand, sometimes it even picks up huge boulders that are in its way and carry it along in the glacial system, we see that rock upon rock creating abrasion and striations and grooves on the bedrock. Imagine having rocks within the ice grinding against the bedrock as it moves by. That's what we mean by some of these erosional features, such as abrasion and striations, and even glacial polish if we have fine enough pieces that are moving over the continental bedrock. Let's look at this diagram, and we see that glacial ice is moving from right to left. Any rocks that are caught up here in the glacial ice, and sand particles as well, will abrade this underlying bedrock. Now, as the ice flows over this feature, and it is an erosional feature, we're actually cutting with glacial ice into the bedrock, it will pick up some of these rocks, glacial plucking, and now that these are encased in the ice, we'll also get some more striations and grooves. This type of erosional feature, if it's large enough, is referred to as a roche-Montagne. And here you see one. Notice the glacial striations, again, rocks incorporated in the ice, and as the ice moved in this diagram, this photograph, from the right to the left, probably also picked up some rocks down below here, downstream as far as the ice goes, and plucked some of this up and incorporated it into the ice. This is a roche-Montagne. Dime for scale, you can see some striations caused by glacial ice. Okay, other erosional features. A glacier system is different from a fluvial or river system simply in its valley. A river system has a V-shaped valley, and a glacial system, it tends to be really broad and a U-shaped valley. Now, what happens in a river system where you have a V-shaped valley and a tributary joins the main river channel? Well, not too much. Basically, you have a smaller system moving into a larger system. It's a little bit different with glacial ice. We may have a huge mass of ice, an alpine glacier, moving through a valley. A smaller tributary of ice, a smaller tributary glacier would join in. Now, if you're looking at it as it's happening, you wouldn't see what's going on down below. You'd see a big piece of ice moving down the valley and a smaller little tributary of ice joining in. However, if the smaller tributary is not carrying nearly as much ice or transporting ice down slope because of gravity, what is really going on underneath is that we have this huge glacial U-shaped trough, and we have a little bitty tributary glacier joining in, so that when the climate warms and the ice melts, we have a big U-shaped valley and a smaller valley that's much higher than the floor of the big original glacial valley. If this smaller tributary valley still transports water, we see a stream moving along, and then when it hits the edge of that tributary valley, we have a waterfall. That's referred to as a hanging valley. Hanging valleys are where the tributary valley was much higher than the main valley. Let's take a look. Here we have a typical glacial trough. Of course, it's not transporting ice right now. There's a little bitty stream running along the bottom. And here we have the main glacial trough down below. This was a tributary valley, but it carried much less volume of ice, therefore its cross-section was much smaller, and although the ice surfaces met, the bottom of the channel did not. So now when water moves through this tributary valley, we have a waterfall as it falls down to the main glacial trough, the original floor. So this would be a hanging valley. We can also have cirques. Remember cirques when we said that this was a round-shaped glacier, but we could also refer to it as the bowl that's left behind. A fjord is a drowned glacial valley. When the sea level rose with respect to the glacial valley, we are now flooding that glacial valley. In this photograph, we have a nice cirque right here. If any of you ski and don't like to ski the trails, but instead you like to take the lift up for bowl skiing, where it's basically a free-for-all in a big bowl of snow, chances are you might be skiing in a cirque filled with snow. This is a fjord. Norway is famous for its fjords. Originally, this was a nice deep glacial trough, but after the climate began to warm and glacial ice melted, lots of it, and moved back into the oceans, well, guess what? The ocean level rose, and the ocean now floods into the glacial trough, so we have a fjord. Horns or other erosional features. Glacial features tend to be very jagged and steep. A horn is a steep-sided peak, whereas an arête is a steep linear ridge, kind of like a razorback ridge. This is a famous horn. This is the Matterhorn, a peak, mountain peak. There's another view. See how jagged? It's not rounded at all. This is a glacial erosional feature. This would be an arête. It's a knife edge, very steep, very indicative, again, of a glacial system, not a fluvial system. Very jagged. Okay, transportation. Glaciers are different from rivers. Whereas rivers can only carry fine sand in suspension, glaciers can carry just about everything they darn well please. As a glacier encounters a boulder, even a huge boulder the size of the room you're in, the pressure would cause the glacial ice to melt as the glacier encounters this boulder. And then, as the water refreezes around the boulder, if the glacier is big enough, the boulder will simply be incorporated in the ice and moved on down the alpine channel. So glaciers are much more powerful. They're the most powerful geologic agent, much more powerful than rivers. When we see glacial ice transporting, we generally see the sediment from the valley floor carried near the base of the ice, and also the sediment that may fall from the overhead mountains due to mass wasting carried on the top surface. Sometimes glaciers look dirty as a result. Here we have a diagram showing, well, down at the bottom, let's look at this first. We are carrying different sizes of sediments as well. We're not sorting. It can be sand, silt, rock size, boulder size picked up along the valley floor. And you can see over here we've had a mass wasting event. That may be a slump or a landslide. And this sediment will now be carried on the top of the glacier. Note here we have a little bitty tributary glacier moving into the main channel. When this ice melts, what will this produce? If you thought Hanging Valley, you were correct. This is Bernard Glacier in Alaska, and you can see a lot of sediment being carried along the top of the ice. Okay, glacial deposits. Now, glaciers are different from rivers in another way. Glacial ice deposits when it melts, right? Okay, so a glacier has boulders and pebbles and sand and silt. And all of this stuff that's in the glacier or carried by the glacier gets deposited simply when the ice melts. So as the ice melts, things start falling out and are deposited directly there. In that case, we get something called till. It's not sorted. It's very angular. It hasn't been polished or rolled around like it would be in a river, and it's only deposited right where the glacial ice melts. A river or running water, on the other hand, deposits as it loses energy. So if you have bigger size particles and medium size particles and fine clay size particles, what a river will do, as it loses energy, it drops the bigger stuff. As it loses more energy within the ocean, let's say, where it meets its end, where its delta is, we see the heavier stuff, and then the sand-sized stuff, and then the silt-sized stuff further away from the shore. Rivers sort. They don't deposit things as a big mumble-jumbo. Glaciers do. Simply as the ice melts, things fall out of glacial ice. Let's look on this slide. We can see that till is unsorted, but if the meltwater from the melting ice sorted this stuff, we referred to it as stratified drift. It's glacial material, but it's sorted by streams or running water from that melted glacial ice. Altogether, till, unsorted, and drift comprise glacial drift, any deposit made by a glacier. Now, this picture was taken on the east coast of England. This is from the Pleistocene epoch, which is the one right before our current Holocene epoch. And this was during the last ice age. This is till. Look at some of the big boulders, as well as some of the finer stuff that's mixed in. It's not sorted. It was deposited right as the ice melted. Now compare this to northern England. We see some sorting going on. In this layer, we see some gravel-sized particles, and here we see finer stuff. Now, this wasn't deposited at the same time. This was an event, and this was an event. But you can see that the material is much more sorted than this stuff. This is till, and here we see sorting going on or stratified drift. Moraines are deposits made directly by a glacier, and they can include end moraines as the glacier ends, lateral moraines on the side of the glacier, and medial moraines in the middle of a glacier. Here we go. We have, this used to be a glacial trough, nice U-shaped valley. These are end moraines. This is where the glacier terminated. These are lateral moraines on the side of the glacier. Drumlins are depositional features as well. They are elongated hills. They're deposited under the ice, and they are composed of till, which means they are unsorted. They can tell the glacial flow by their shape. Let's take a look. This is an old diagram, but it's one of the best I've found that shows this feature. Here we have a drumlin. It looks like the bowl of an upside-down spoon, and basically the bigger part of the bowl is up glacier. The more gradual slope of the drumlin shape points toward the end of the glacier. It's formed of till. This would be the unstratified drift. Now, let's look at this photograph. This is a drumlin. It's composed of till. It's a depositional feature. In which direction was the ice flowing? Well, if you believe the ice was flowing from the right to the left of the photograph, you're correct. The bigger part of the bowl with the steeper slope points in the upward direction of the glacier, and the more gradual slope points toward the end or the terminus of the glacier. There are different water bodies associated with glaciers as well. An estuary is left behind by a river flowing underneath the glacial ice. It's stratified drift because, one, it was deposited by flowing water and not ice, and water does sort material unlike ice. However, the ridge is deposited while the glacier is still present. So we actually end up with a ridge feature as opposed to a channel or a feature that is scoured out, an erosional feature. A torrent would be a small lake in a cirque, and we also see kettle lakes that are associated with glacial systems. Let's look at those. Here we see glacial ice, and at this point it looks like we are at the end or terminus of the glacier. There are some sediment-filled depressions here. When the glacial ice melts, you can see this ridge. It would be stratified drift because it is going to be deposited by running water that was flowing underneath this glacial ice. This feature is referred to as an esker. Now, we've already looked at drumlins. And although this diagram is not very, very clear, since we know that the ice was flowing from north to south, we know that the more gradual slope would be toward the south of those drumlins. Now notice what happens as the glacier retreats. There are some big pieces of ice that are left behind. And what these pieces of ice do, they depress the sediments underneath them. Now as the climate warms, the ice melts. So we have a depression which is filled with water. That would be a kettle lake. Here is an esker. Again, the glacier was over this area. The river was flowing underneath, and the sediment that was deposited would be stratified drift because it's deposited by water. Here is another overhead diagram showing the esker. And here we actually see a delta that was formed as this water met its end, its terminus. Here are some kettle lakes. These were once depressed by huge blocks of ice which subsequently melted. Okay, now when we're looking at a topographic map, how do we know we're even dealing with a glacial system? Well, there are a couple of tips that we can use. One, if it's an active glacial system, the ice or the snowfall will actually be drawn in. You might actually see a white area where the glacier is moving through. Some other things to look for, though, if a glacier is not present, if it has melted, you get very sharp features, very steep ridges, and very sharp peaks. Have horns, those steep peaks, and arêtes, those linear ridges. You may also see a lot of small kettle lakes where ice has depressed the sediments and subsequently melted and filled up these nice little lake systems. Okay, some of the tips, again, we want to look for those U-shaped valleys, very different from a fluvial system where we have a V-shaped valley. Those steep-sided ridges, those are arêtes. The short peaks, those are horns. The numerous kettle lakes, and we can also look for depositional features such as moraines or drumlins. And again, the drumlin can tell us the direction the ice flowed originally. Let's take a look at a couple of topo maps you may encounter. Okay. Now, this is a system. It doesn't look like any ice is present now, But you can see from the contour lines, they tend to be more widely spaced in this area. And if you had a close-up view of this and you took the time, you would realize this is lower elevation. This is a glacial valley. And if you take a cross-section of this, you would see that it is in the form of a U shape. Actually, you may be asked to do that on this map. Now, look how sharply some of these ridges are defined. These contour lines are extremely close together, so we have a very steep knife-back ridge. This would be an arête. We also have a couple of peaks. This one almost looks like a strange star pyramidal shape. There's another one down here, very steep peak. And we know it's a peak because our contour lines are close together and we're getting higher contours as we get toward the center. So these would be examples of horns. Now there's one more thing I'd like to show you. If you look up here, let me bring this down a little bit. We have a little lake here. This actually may be a cirque lake or a torrent. So we have the little stream moving along, and then we hit an area right about here where there is a rapid drop in elevation before it moves out and joins another channel down here. Since we have a rapid drop in elevation, this would be an example of a hanging valley and a waterfall that's produced. Originally, this was probably a tributary of a main glacier system. Let's look at one more map. And what I'd like you to see on this one, this is a glacier system. Notice how we're colored white, and it's called Harvard Glacier. What do you think all this brown stuff is on top of the ice? Let's go back to an old PowerPoint photograph that we looked at earlier. This is of Bernard Glacier. Remember we talked about the sediments that were transported either on top of the glacier or on the bottom? Look at the brown versus the actual photograph. So this is debris, sediments that are transported by the glacier and probably will end up with moraines later on when the glacial ice melts. Well, that will conclude our presentation today on glaciers and glacial landforms. If you have any questions, please feel free to email your instructor. He or she will be happy to answer any of your questions and help you understand the material. Thank you very much for joining me, and have a great day.